I'd really like to thank Chad and the organizers for asking me to come here and talk about a topic which seems so fundamental, but yet sort of is really onerous for a lot of graduate students who are getting started in NMR, trying to get their sequences working and understand how things work. So Chad made the title, and I thought, really this talk is about P pathway selection. And if you don't know what P is, don't worry, that you're in the right place. Okay. Well, there are two, really, in this field, two systematic ways to select P pathways. And the first is simply to exploit a well-known Fourier relationship between the delta P that occurs during a pulse and that pulse's phase. All right. And the other way is to use pulse field gradients. Now, this is a talk on phase cycling, so I won't talk about the second, using pulse field gradients, but it's also a very powerful way, and you should learn how to do that too. So this talk is about the first part one here. Now, when you're using phase cycling or using pulse phase, there's an easy way to do it, which I'm going to tell you about, and no one does it this way. But it's the easiest way to conceptually understand what's going on. So I want you to understand it first, and then we'll work on the hard way, which is through receiver phase cycling, which is what everyone does, and I'm not going to talk about. But I've left in my notes, I've been giving this talk for over 20 years, and I left in my notes all my extra notes on how to do this with receiver phase cycling. But I hope maybe by the end of this talk, you won't want to use receiver phase cycling anymore anyways, because you don't have to. Okay, so I only have 40 minutes, actually maybe only 25 now. So I'm going to just present 1A. Okay, so for the students out there, anytime you sit down in front of the spectrometer, you really have simple tasks in front of you. First, you need to think, what is the spin system that I'm going to be exciting? Okay? What are its energy levels? And what are all the possible transitions that I can excite? Okay, just try to get those straight first. So I'm going to walk through some very, very simple examples for you. Okay, an ensemble of uncoupled spin half nuclei. You only have two levels. And we have only two possible transitions. I think I'm supposed to use my mouse here. So we can excite from plus half to minus half, or we can excite from minus half to plus half. Only two possibilities here. Now, in NMR, we classify transitions by their p-value. So what's the p-value? The p-value is just simply m final minus m initial. So this is p, m final minus m initial. So we will classify transitions by their p-value. So we're having a transition from m to m plus p. Okay? And there are going to be lots of transitions with the same p-value, many transitions with different p-values. All right. So anytime you do an NMR experiment, you can only observe a transition with p of minus 1. This p plus 1 transition you won't be able to detect. All right. Now, if I had a spin 1, well, there's three levels, plus 1, 0, and minus 1. And there's only two transitions that we can observe, but you can see now there are four transitions we can observe. So there's not only the p plus 1 transitions, but there's also two double quantum transitions with p of minus 2 and p of plus 2. All right. Now, if I go to spin 3 halves, I get even more transitions. So you can see that what you observe is just the tip of the iceberg of all the transitions that are present in an NMR spin system. So we detect these p equals minus 1s, but there's also the plus 1s, the minus 2, the plus 2s, and the plus and minus 3s there. We can only detect these minus 1s. Okay. Now, a lot of you aren't interested in quadrupolar nuclei, but so let's stare very hard and carefully at this. This is just two coupled spin half nuclei. There are four transitions there, four energy levels there, and these are all the transitions. Now, we can only observe these over here. Now, note, okay, that there's two nuclei, A and X here. So we can observe A with a PA of minus 1 here and here, or we can observe X with a PX of minus 1, but it always occurs with the other guys equal to 0. Okay, those are the only ones we can observe. And then all these other ones over here, including the double and zero quantum transitions, we're not able to observe. Okay, so again, identify your spin system, identify the levels, and all the transitions that you have in your system. Now, when we're looking at homonuclear spins in the experiment, we were going to be interested also in the sum of these p's. So we're going to be interested in PA plus PX in this case. All right, let's make it even harder, and then we'll stop with this part of the lesson. So if you have 3 coupled spin halves, then you have even more energy levels. And I'm not going to draw the ones you can observe because it's quite a bit. So these are the ones that you can observe. But we still have the same rules that we can only observe, in this case, PA, PM, or PX of -1, while the other guys are equal to 0. So one of your assignments here is just to look for all the transitions that have a sum of PA plus PX plus PM of -1, but are not detectable. All right. So for these observable ones, we're going to get a multiplet for the A's, a multiplet for the M's, and a multiplet for the X. Those are the transitions you'll observe in the spectrum. All right. Now, when you do an NMR experiment, you're applying a lot of pulses. And when you do that, you're exciting transitions. And when you apply the first pulse, you excite a transition. The next pulse will move the coherence associated with that transition to another transition. The next pulse will move that one to another transition. So we do this hopping from transition to transition to transition to transition, and eventually we get to a transition where we turn the receiver on and we detect the signal. And the phase of the signal that we detect depends upon the history of all the transitions that you lived in on the way to that observation. So it's a very simple relationship here. I have down here, and you can see just the frequency times the time spent on each transition added up over some total time period here. That will give you the phase, and we can also just calculate an average phase. You can think of that as average frequency theory, and that's the frequency of the spin system after all these pulses from this point to this point here. All right. So there are many transitions that you can generate when you apply a set of pulses. When you do your experiment, you're going to be interested in maybe one transition or a subset of transitions, and then there will be a whole bunch of other transitions that you don't want. Those are the signals that are going to complicate, cause artifacts that you need to get rid of. So you have to think about, now you've identified your spin system, what are the transition pathways that have my signal, and which ones do I want to make sure I don't detect? So let's go back, very simple again, to just spin half system. Let's just look at an ensemble of uncoupled spin half and 2 pulses. How many transition pathways can we have in that experiment? Well, you start out, of course, equilibrating. So the equilibrium state, I should maybe change this to polarized, because who knows how we do it. The equilibrium state has P of 0, and then you can apply a pulse. Well, the first pulse can excite a transition up. Remember, this is just spin half. And the second pulse can move you to another transition up. Okay, that's one possibility. You could go down and then up. Or, for example, you could just rearrange. The first pulse could just rearrange your populations and then excite you to a transition, in this case up. And then you can have the equivalent possibilities here, so up and down, or down and down, or just a rearrangement of populations and down. So those are all the transition pathways that you could have for 2 pulses on an ensemble of spin half system. And you see I have written down the p-values for all of these guys, for all those transitions. So in the notation that we all use is to simply just not do a diagram like that, but do a diagram like this, where we trace out what the p-values were throughout this pulse sequence. Now, when we do this experiment, I said we can only detect p of -1. So that means that we can only observe those transition pathways. The ones below all ended at +1. We can't see those. So we only have 3 transition pathways that we can observe here. And those correspond to 3 experiments you probably already know. Certainly you know the Hahn-Echo experiment. Certainly you know there's magnetization recovery experiments. And you might not be familiar, but there's also the anti-echo experiment, which is the pathway at the top, which you'll run into. So that brings us to the second step. Once you've identified your spin system, you have to decide, okay, this is the transition pathway I want to detect, and I know its pathway. Now I have to figure out how to get it away from the other guys. So let's say we pick the Hahn-Echo. We want to do a Hahn-Echo experiment, and it's on a spin half system. So you know you have 2 pulses, pi over 2, pi pulse. Now I'm putting in the pulse lengths. And so this is the pathway you want. Now, at this point, it's important to realize that a pi pulse is very special in NMR. It has the effect of taking you from a transition of M initial to M final to a transition of minus M initial to minus M final. That is generally true. So a consequence of that is if you calculate what happens to a P when it undergoes a pi pulse, is that these guys change sign, so it means the P will go from a plus value to opposite in sign. So that's the effect of a pi pulse. So when we do a Hahn echo experiment, we use a pi pulse here at the very end. And if that's a perfect pi pulse, then we can only observe -1. And if this requires us a full change of sign, then it's impossible for those other two pathways to even get into our receiver if we have a perfect pi pulse. So there, you've done pathway selection. You can stop right there in this particular case. You just had a well-calibrated pi pulse, and you've done the job. All right? Now, in practice, it's not going to be a perfect pi pulse. You're going to have, maybe you didn't calibrate your pulse lengths right. Maybe there's offset effects, RF homogeneity. There's all kinds of reasons why that pi pulse may not be perfect. And when that happens, then you're going to get contamination from those other pathways. These two guys are going to start to show up, and you don't want them there because they're going to complicate your spectrum and make weird peaks, and you need to get rid of them. So how do you get rid of these guys? Okay, so here we are at the hardest part in terms of the math of understanding this. The first thing to realize is before you turn the pulse on, when you're just evolving freely, that the Hamiltonians that you experience, the offset, the J coupling, the quadrupole coupling, the dipolar coupling, these guys are all invariant under rotation about Z. So they don't care about any kind of rotation about Z. When you turn on the RF pulse, that's perpendicular to that. And that RF pulse term there is when you change the phase, you're rotating the RF pulse about the Z axis. So if you pulse along X and you want to pulse along Y, you're just doing a rotation about Z. So since the internal Hamiltonian doesn't care, by changing the pulse phase, you're changing the entire Hamiltonian. You're rotating it about Z completely. So that means that the entire Hamiltonian, as a function of pulse phase, is just the Hamiltonian with the pulse phase equal to 0 rotated about Z. So that means that you can do the same with the propagator. The propagator with the phase 0 is equal to the propagator. We rotate that one about Z, gives you the propagator for an arbitrary pulse phase. So if you take a given transition from M to M plus P, then you know how to calculate this. You say you take that transition and you sandwich it between the propagators. You expand it all out, do a little bit of math, and what you end up with is this result here. Now, don't worry if you don't fully understand this. I'll simplify this. But it just means that if you start out with a transition of P0, then a pulse is going to split you off to a whole bunch of other transitions with different P values. And each transition that it split you off to is going to be modulated by a phase of delta P times the phase of the pulse that did that. And so delta P is the P value you had before the pulse, and delta P is P1 minus P0. So P0 is what you had before the pulse, and P1 is what you had after the pulse of those many possibilities there. So what does this mean for you guys? We're just getting started. Very simple. It translates to this. If you acquired the signal as a function of the pulse phase from 0 to 2 pi, and you Fourier transformed, you would get the delta P's. You would get a spectrum that's a delta P, spectrum of delta P's that occurred during that pulse. Now, you're used to doing a Fourier transform with respect to time and getting the frequency. But you know how to do this. It's the same command, ft, and if you just had a phase dimension, you would do the Fourier transform, and you would get a spectrum of delta P's that occurred during that pulse. Very straightforward. This is a very old idea. It's been around for a long time, and goes back to the 70s. And this was really fully exploited when multiple quantum NMR came around. So at the time of multiple quantum, this was essential for understanding how to get multiple quantum NMR spectrum. But it's very much more general than that. So now we come to final step 3. All you have to do now, you've identified the spin system, the transition pathway, you know the P pathway. You just need to acquire your signal, not only as a function of time, but as a function of path phase, do the Fourier transform, select the delta P that you want, and you're done. That's it. So I could stop here, and we don't have to finish, go anymore. I can save time because of the other lecturers here. So anyway, let me just go and do some very go back to simple examples, back to spin half again, and we're going to do one pulse acquire with a pulse that has a phase, phi. Now, you're going to acquire this signal as a function of time, of course, but also as a function of phase. So this is a transition pathway. There's the P pathway. If I Fourier transform this, well, if I Fourier transform with respect to time, I'll get some resonance, just say there. If I Fourier transform with respect to pulse phase, I'm going to get a delta P dimension. And it will range, if I do steps of pi over 2, it will go from -2 to +2, with plus and -2 being aliased, okay? But what we know now is that this experiment had a delta P of -1. So in this dimension, this experiment will have a resonance here at delta P of -1. And everything else will be zeros. These guys won't show up, and only there will we have our signal. That's it. Now, you're probably thinking, all right, that's kind of a stupid 2D experiment to do that. All right, so why would this be helpful to me? All right, so let me just take you back a bit. When I was a kid doing NMR, when we sit down at the spectrometer, we took a spectrum, we didn't just get the spectrum of where the resonances were, we actually got ghosts in our spectra. And so back in the 80s, we didn't have receivers that were as good as they are today. So you wouldn't know about this, but there are many of us in the room that remember this. So we have to get our signal mixed down in quadrature to X and Y, real and imaginary channels. And in the 80s, our quadrature detection was done analog fashion. So we had to mix the signal down, and sometimes it wasn't done right. So instead of the X and Y in the rotating frame being orthogonal, there was a little bit of an error there. And because of that error, we would get something called quadrature ghost. Okay? Now you have digital quadrature detection. It's done really fast digitizing. This has been eliminated. But just humor me and let's think about this. Also, even today, you're going to have some kind of baseline offset. There's going to be some signal, some constant signal that's going to be there. When you Fourier transform, it's going to be a spike at 0. So here's two problems. So when you have this quadrature ghost, the effect of that is to actually allow you to detect a little bit of P equals +1. I said you couldn't detect that. Well, the answer is if you have a bad receiver, you will detect a little bit of P equals +1. So you need to get rid of that. That's not good. So instead of seeing a spectrum where you just have your resonance there, that where you expected it, you see what I have down here is you get some spike at 0 and you get some ghost over here. This is pretty bad, but sometimes it can be this bad. So how do I get rid of this ghost? And they're going to always show up at mirror image frequencies. So I just gave you the answer. If you acquire the signal in a one pulse experiment as a function of pulse phase, and you do that double Fourier transform, then the ghost will show up here at delta P of +1. And the offset noise, the baseline offset, will always show up at 0. And your signal that you want is there at P equals -1. Okay. So this is it. This is how you separate your signal. So you take out that cross-section, just pull out this cross-section, and you're done. You've done the phase cycling. In this case, though, we're not doing phase cycling. We're just doing a Fourier transform with respect to the pulse phase. But this is the essence of phase cycling. This is all you have to do in order to separate your pathways. Once you understand this, then the rest is just more applications to this. So let's look a little further. So let's go back to two-pulse experiment, a Hahn-Echo experiment. Here we worked through this before. We know the pathway is a delta P of +1 and a delta P of -2. That's the pathway. If I made each of those two pulses a phase dimension, so a phase dimension for the first pulse, a phase dimension for the second pulse, and then I did a double Fourier transform with respect to phase, let's forget about time for now, just took the time origin at points, cross-section, and looked at the delta P 2D signal here, then you see that for delta P of +1 and delta P1 of +1 and delta P2 of -2, I have this peak right there. That cross-section, if I pulled out that cross-section, that would be my Hahn-Echo signal. But I also would have a peak here that would be any contamination from a magnetization recovery experiment or the anti-echo signal. My ghost would be over here. And the baseline offset, no matter how many phase dimensions I have, is always there at 0, 0, 0, 0 in all of these cases. All right. So I know what you're thinking. That's a lot of phase dimensions. Do I really need all those phase dimensions? Well, I'm going to show you that you can reduce that down quite a bit. Maybe not all the way down to 1 dimension, but a lot less than the number of pulses that you have. So just look at that 2-pulse Hahn echo experiment to give you a simple example. If I got rid of the ghost, this is what we were dealing with. Okay, so this is everything that could have happened in that experiment. And you can see that if I just project it up, that actually then this signal, the Hahn echo signal, would have been separated, and I only needed 1 dimension. So that already tells you that I could have left the first pulse at x and only made a phase dimension for the second pulse, which would have been equivalent to projection up, and I would have had it separated. So I've already reduced it by 1. Likewise, you could see the same thing would have happened if I only made the first pulse a phase dimension and left the second one x. Then I would have projected out the other way, and I would have got it separated. So there I would have needed two phases. Actually, there's another way to do this, which I think is kind of fun. And this is the way that we try to take even more complicated experiments and reduce them down to just a few number of phases. So this is a very simple rule. Anytime your delta P is positive, just use a single phase and make that phase positive. When your delta P goes negative, take that same phase and make it negative. So no matter how many pulses you have, if the delta P is positive, make it positive. Anytime it goes negative, positive, negative, just change the sign of that one phase. And the effect of that is to just push, you get an accumulated delta P, it will push your desired pathway off to the edge of the delta P spectrum. So in this case, it picks up +1, but because I changed the sign here, and this is minus, it picks up another +2, so it pushes it out here to +3, and all the bad guys show up over here, nicely separated. So then I just do a Fourier transform, and I have it gone. Now, in this case, I had ±4, so I had to have a step of pi/4 to get that wider spectral range. But if I got rid of the ghost, I could go back to just steps of pi/2 for my phase dimension. All right. Now, let me show you a nice example recently we did to do this, which was simply that in Carr Purcell, Myboom-Gill experiment, CPMG, in practice, we think every pi pulse is going to give you a perfect refocusing. And so you should have 2 pathways, P pathways, that will occur with even and odd echoes occurring for these 2 different color pathways there. But in practice, the pi pulses are not perfect, and so they knock a little magnetization back along Z, and this happens over and over and over again in this experiment. So you end up with a lot of stimulated echoes, and it looks like your echo train just never wants to die, even though it's longer than T2. But that's because of all these stimulated echoes that get mixed in. So you need to get rid of them, but that's a lot of pulses to phase. But so what I just said is that you can just push the desired ones off to the edge with single phase. And in this case here, what we do is we just say, well, the green paths are going -2, and the red paths are going +2. Every time you go through this loop, the green ones will accumulate an additional -2, and the red ones will accumulate an additional +2. So the first echo shows up for the red ones, or the purple ones, there at +2. The next time through, it goes to +4, and then +6. Whereas the green ones show up first, the first echo -2, then -6, then -8, and so on. And that pushes the bad guys, pushes the good guys off to the edges and leaves the bad guys inside. So if I made just bad pi pulses in this, maybe they're 120 degrees, then you'd see all the bad guys showing up here because you've lost your signal. The really cool thing about this is of not phase cycling is that you get to see where your signal went when your experiment's not working. So if you say, why am I not getting the echoes or signals that I'm supposed to be getting? Well, if you have phase dimensions, you see that's where it went. All right. So this is great for us because now we can measure J couplings in one pulse train. If you try to do J couplings with CPMG, you got all those stimulated echoes. You always got a big spike at 0. Sometimes your J coupling was on, sometimes it was off. It messed up your multiplet structure. But with pieta, with these phase dimensions, you can get nice multiplets there that are accurately measured. Okay, so the way I've described it is fundamentally there's a thing called a transition pathway, but we're phase cycling, or we're doing phase dimensions to select P pathways. But P pathways and transition pathways are not equivalent. There are many transition pathways different that will map to the same P pathway. So if you want to understand what's going on in your experiment, you have to think more about the fundamental transition pathway and make sure you keep track of all the other things that could happen. It's not just P that's relevant in your experiments. So chemical shift, everyone knows, And I've written out the expression for the frequency here. And of course, there's an isotropic part. There's, for the solids people, there's an anisotropic part with this complicated orientation dependence here. But the key thing is that the chemical shift only depends upon P. So when P changes sign, goes +1, +2, or -1, -2, chemical shift is all along for the ride, and it's changing sign and scaling just like P does the whole way. All right. But take something like the first order quadrupolar interaction. That contribution to the frequency doesn't depend on M final minus M initial. It actually depends upon M final squared minus M initial squared. So not P. It doesn't depend on P. It depends on this thing called D, we'll call it. And it has the same kind of orientation dependence. But if you look at the two transitions, then you see that these two transitions are both P of -1, but the D values change sign from plus square root of 3 over 2 to minus square root of 3 over 2. And that's why the powder pattern here has these two transitions with mirror images of each other, because it's the D that's changing sign, not the P. And remember what I said about the pi pulse having the special property, general property of giving you M final, M initial going to minus M final, minus initial. So it's one transition to only another transition. It's not splitting into many. The effect of that, as I said, was changing the sign of P, but because these guys are all squared in the D, that these guys, the D's stay invariant to a pi pulse. So if you have a D contribution in your frequency, it will not see that pi pulse at all. It'll go right through. So here's an example. If you take the Hahn echo and you try to do that on a first order quadrupole pattern like deuterium, then when you apply the pi over 2 pulse, well, you'd excite these single quantum transitions, and the pi pulse would do its job, taking this transition to that one and that transition to that one, and it would make the P's change sign. But if you look at this, you see the D's stayed the same. So I'll draw another diagram down below to say, well, the P's change sign, but the D's are constant in this. So they didn't refocus into an echo. If you want to refocus the first order quad into an echo, it's not a pi pulse that you should use. What you should use is a pi over 2 pulse. That will allow this transition to jump over here to this transition where P doesn't change sign, but the D does change sign. And it will also give you a transition pathway where this transition hops over here and the D changes sign. So now you have two transition pathways where P doesn't change sign, but D changes sign, and you have what we know now as the solid echo. A solid echo is a D echo, M final squared minus M initial squared echo. Okay. But that's not the whole story in this pi over 2 experiment. A pi pulse has a simple transition to transition mapping, but a pi over 2 pulse spreads you out to all transitions. So this is only a subset of what could have happened with that second pi over 2 pulse. I could have also moved this transition to this transition and this one to this one, and that would have given me this subset of pathways where P doesn't echo and D doesn't echo. So that would have been, I call, a no echo sequence. For deuterium with a wide pattern, you probably wouldn't observe that because it would have dephased very quickly. Or you could similarly do this pathway where you change them like this, and you can actually make P and D simultaneously echo. So say we have a 2-pulse sequence and all these possibilities, and there's really maybe only one of these that you want to detect, and you don't want the other guys there. But just selecting a P pathway, particularly like this one or the one here, this one and this one are two different experiments, but they have the same P pathway. So that's my warning to you. The P pathway does not uniquely define your experiment. There may be other transition pathways that you don't want that have exactly the same P pathway. Okay, away from the quadrupoles, again, back to the spin half nuclei, let's just take something like the Cozy experiment. So you have two coupled spin half. The frequency is here. I got rid of the anisotropy. So now we have spin A and X. We have the isotropic chemical shift here. And we have the J coupling. The J coupling is just like that first order quadrupole coupling. It doesn't depend on P. It depends on something I'll call D again. It's MA final, MX final minus MA initial, MX initial. And that, again, is going to be invariant under a pi pulse applied to both spins. But I'm not interested in that experiment. Let's look at the correlation spectroscopy, where I have a pi over 2, pi over 2. The first pulse will excite all the observable transitions. Actually, it will excite all the single quantum transitions, but let's just excite, in this case, we're only going to excite the observable ones here. That's what we're interested in. And then the second pulse will transfer those to the same set of transitions. But what happens is A1 gets transferred to A1. It also gets transferred to X1. It gets transferred to A2 and to X2. So that's 4 transition pathways. X1 goes to X1, X1 goes to A1, X1 goes to A2, X1 goes to X2. That's another 4. Count them all up, there's 16 transition pathways. And in COSY, we know there are 16 lines in a COSY spectrum. That's the 16 transition pathways. So if I just looked at 4 of these, just so you can see that the A1 goes to A1 and it can go to A2. I write down PA, PX pathways. I can write down PA plus PX because that's the one that's relevant for my phase cycling or my phase dimension. And then, but you can also see what the J coupling is doing in terms of what this D is doing. And here's the other 2 pathways, other 2 transition pathways too. So you can work out all of this, and when you're done, you can see that all these 16 peaks belong to the 16 transition pathways. But you can see the critical thing is that they all 16 of those have the same pathway of PA plus PX equals -1, -1. All the same, but they have all these sort of different sort of histories there. Okay, the light's yellow, and I'm going too slow. So let me just tell another case where this is really important to understand this, and that's line shapes in multidimensional NMR. This is another common problem. We have these phase twist line shapes that we need to get rid of in multidimensional NMR, and because they make it harder for you to resolve peaks that are close to each other. We rather go to pure absorption mode line shapes. And the problem is that when you have multidimensional and you do a double Fourier transform, you mix in dispersion modes into the real channel. And the solution is absolutely simple. You just have to take those integrals, which I had in the previous page here, and move that lower limit to -infinity. That's a piece of cake. Just change it from -0 to -infinity, and the dispersion components go away completely. In fact, you only need to move one of them because you'll keep them segregated there. But in practice, that means you need to acquire signal before the pulse, and that violates causality. So that's not going to work. Okay? You can't have negative time. So what we have to do is trick the sample, trick our experiment into pretending like we have negative time, even though we don't. So you may have a transition pathway where you have this transition and this transition for T1, and you know all the pathways that are associated with it. What you need is a transition that has the opposite frequency. And so if this is the path you want, then you find another pathway where during T1 you have the opposite frequency. You move that negative sign over to T, pretend now that you're acquiring negative time with a positive frequency, and that's the signal going backwards in time. That's the hypercomplex trick for getting a signal going backwards in time. That allows us to get this quadrant, so we can now Fourier transform from -infinity to +infinity. All right? So that's how you do hypercomplex, but you need to get the other pathway. So for example, let's take again spin half system, but 2D exchange experiment. The 2D exchange experiment should be, it's like a stimulated echo experiment, but not. It's actually P equals -1, P equals -1, and then the anti-pathway is going to be the stimulated echo experiment of +1 and -1. So we need to acquire both these pathways to get the 2 quadrants of T1, positive and negative T1. So when I know my receiver's detecting -1, so I'm not going to phase this last pulse. I'm going to leave that one at X. And for these guys, since this goes up and that one goes down, I'm just going to make this one positive phi and that one negative phi, and then I can make it into a one-dimensional experiment. But for purposes of explaining this, let's make these separate phases. Now, if you look at the 2D delta P1, delta P2 experiment, you can see here's where all the signals are. The one that we want, which is the pathway, is this one right here of -1, +1. And then the other one that we want with the negative time is right here. And then you can try to work out why these other ones show up here from all other possible pathways. But if you did a double Fourier transform, you just click here and then click here, you would just pull out the 2 cross sections, which is the positive and negative time quadrants. But as I said, you could make these just phi and -phi. You can make a one-dimensional experiment where you just do one Fourier transform with respect to phase, click here and click here to get the positive and negative times, and you're ready to do the rest of your hypercomplex processing there. All right, I'm going to try to finish up with this last example here, which is, this is really common. It is a way to generate 0 and double quantum coherence is in a 2 coupled spin half system. You apply a pi over 2 pulse, you excite the single quantum transitions, and you let them evolve for 1/4J, and then you apply a pi pulse. Remember, the pi pulse has this special property of taking this transition and making it only that transition. this purple transition there, the gold one there to there. So we can work out all the transition pathways, and we get to the end of this period, and we apply a final pi over 2 pulse. Now what happens here is kind of magic. If you set these tau times exactly right, it's 1 over 4j, then what happens is the last pi over 2 pulse causes all these transitions to go to all the other transitions. But what happens with this special timing is that these guys, when they move over in pairs that are 180 degrees out of phase with each other. So this one may move over here, it may move over here, it may move over there. This one may move over there, but it cancels the other guys as they come over. So the result of this is when all of these guys come over, the single quantums all are out of phase and cancel each other destructively, and the only ones left standing are the double and the 0 quantums. All right? So that's a classic block that we use all the time. And you can work out the transition pathways for that. So in an inadequate experiment, we do that to generate double quantum, because that's where we want to have our T1 evolution. And then we apply a final pulse to go back to single quantum. So you can work these all out for the PA plus PX pathways and see what this is. Since I'm out of time, I'm just going to show you then how I would do this experiment, because this is a little bit more complicated. So here's the positive T1 quadrant for an inadequate. Here's the negative T1 quadrant for an inadequate. The first part of this sequence is just +1 and then -2, and then the other pathway is -1 and +2. So I'm just going to make these first 2 pulses one phase. That's just phi and minus phi, because this one goes up and then down, that one goes down, that goes up. That means they're going to accumulate to plus and minus 3, those 2 pathways. The same in the negative quadrant. This one does a little weird stuff over here. It goes to -1 or minus 3. So I'm just going to make that one a separate phase. And then I'm going to do a double phase transform. Do those lights come on in my face because I'm out of time? I'm blinded suddenly. So I'm going to use this third pulse. I'm going to put a phase here, so another dimension. And then when I do a double Fourier transform, I can see the dots here. So I could actually, we do this in my lab all the time. You'll see the double Fourier transform. You'll see all these dots. You just click on this guy, you get one pathway. You click on that one, you get the other pathway. This one and this one, you get the anti-pathways. And then you continue processing. But what's cool about this is if you've made a mistake, something's not working, then you might see that you have more signal on some of these other guys. And the thing about phase cycling, since I'm almost out of time, is that you throw all that information away when you phase cycle. If you keep the phase dimensions, you know when something's going wrong where that signal went. How many times have you stood in front of the spectrometer and watched your signal grow, 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 and then die, 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 grow, grow, die, die, and then it's gone? Like, where did it go? Well, if you had a phase dimension, you'd see where it went, okay? So I'll just sort of end up here saying that you understand the basic idea. If you want to do receiver phase cycling, you can do that. I have extra notes to show you how to go about avoiding the Fourier transforms and projecting it all down with the receiver phase. But the key idea is that if you're writing pulse sequences, this is easier. You might even be able to write one sequence to handle like many multiple quantum experiments without having a special 3 quantum or 4 quantum experiment. So it sort of cuts down on your number of sequences. But it makes it easy because you don't even have to think about solving for that receiver phase anymore. Just forget about, like, oh, what's the receiver phase supposed to do? Just make a phase dimension. The other nice thing is, so if you're writing sequences, that's a big advantage. But if you're doing the experiment, the big advantage is when it doesn't work, you can see where the signal went. And so it shows you where your magnetization ended up. All right. So there's a lot of really good papers to read. But seriously, it was all worked out. It's a very simple relationship that was worked out back in the 70s. But the idea is we just didn't have the disk space, okay? If you remember those big disk platters, right? We didn't have the disk space to save phase dimensions. But now we really do. I mean, we can download all kinds of data from Panama really quickly. So we should be able to do this with our phase cycles. So just a couple other papers here from my group here about the way we do this with pathways. So I want to thank you for your attention. I also want to thank a lot of the guys in my lab who have been worked really hard in trying to get these ideas worked out. And I've had really been happy to have some really great undergrads who have gone on to great places, and some PhD students who have also gone on to great places and done some great work here on this work. And then, of course, I've always been lucky to have Jay Baltusberger down the road in Berea College, who comes up every now and then, spends time with us, and we just chat and work out all these kind of fun things. So, oh, and don't forget, of course, if your software doesn't handle more than 2 or 3 dimensions, you can always download my my app, RMN, which does essentially an infinite number of dimensions if you have infinite memory, and you can do any number of phase dimensions you'd like. So with that, I'll thank you with your time, and thank you for your attention, and be happy to answer questions.